This video is to help anybody who has either been absent for pedigrees for the start of it or who just needs to catch up or get some help. So we're going to start off with the symbols of pedigrees and what each of them means so that when we go and look at pedigrees in a minute, we'll know what we're looking at. So we're just going to kind of breeze through these. First off, you have a male. Males in a pedigree are represented by a square. It could be a shaded in square like this individual, or unshaded or half shaded, but that's representing a male. In contrast, females are represented by a circle. Affected males and affected females means that you have an individual in this family, we're always tracing a family, that has or expresses the trait. So that could be as simple as eye color, and it could be as complex as Huntington's or Parkinson's disease or color blindness or genetic disorders that show a mutation. Next, we have siblings. If we look at this pedigree below us, we have two individuals connected by a line. That typically for us means marriage. So when you have two people connected in the middle of their symbol, that's showing a marriage. And then you have a line coming down and two individuals below them. And that's what siblings are, or children of a marriage. So when you have a line coming down from a marriage, and then you have kind of 2 or 3 or 6 different options, those are your children. And the other thing you could see, and it's not as often, and there's actually other twin options, is if you have twins. Typically the most common you'd see is one arrow, since the most common is one egg splitting apart, and you have two different siblings or twins connected. And then the last one on here is deceased, which we use with a line to show that that person is no longer living. And then the one that we missed on here is a carrier, which you're not always going to see, but sometimes you will. And that we use a half shaded symbol to show that we have a carrier. And like I said, you're not always going to have that on a pedigree, but when you do, it can be really helpful. So we need to use that to figure out if something is X-linked, autosomal, and then recessive or dominant. So we have kind of these 4 different options: X-linked recessive, X-linked dominant, autosomal recessive, or autosomal dominant. So these 4 examples below are looking at those, and we're going to kind of talk about what that means. So when you have a trait that is X-linked, what that means is that you have some kind of mutation on the sex chromosome. And in this case, it's the X chromosome. I'm just going to write chromo for short. So that means for your parents, you get X and X for females, and then X and Y for males, right? So that means on these X chromosomes, that's where the trait's being passed, aka it's linked on the sex chromosome. The other option we have is autosomal, which basically just means the opposite. Autosomal, and feel free to pause if you need to write stuff down and kind of take some notes, but autosomal is a mutation. The way I like to think about it is a mutation on an allele. So not on your sex chromosomes, that's more like everything we've been talking about in Punnett squares. So if you think about your heterozygous alleles, your recessive alleles, homozygous recessive, or homozygous dominant. So when we look at these examples up here, you have to also think about the difference between dominant and recessive, right? When you think about the Punnett squares we've been doing, you have a lot more cases of dominance in genes than recessive, since typically not as many of us carry that recessive gene. So a really easy way to tell the difference for autosomal dominant and recessive is how often you see the gene. For dominant, you're going to see it probably at least half the time or in most of a family, and that family is represented by this whole pedigree, right? So in this case, we have 1, 2, 3, 4 individuals. And out of those 4, 1, 2, 3, all have this trait. So we know that it's dominant because of how often we see it. When we look at the one next to it, the complete opposite, you only have one individual with this trait. And if you think about those Punnett squares you've been doing, if you made a Punnett square for this, this would be a really good example of when you cross a heterozygous and a heterozygous individual, right? You have 2 capital A's here, you have your recessive traits here. This box is really small. And then your 1 lowly recessive trait, right? And that's completely represented by this individual here. So we know, based on that, that this is recessive just because it's not very frequent in this family. And then we have to figure out, is it X-linked or is it autosomal? The way you can tell that is how it's passed on in its family. So the cool thing about your X chromosomes is that everybody has them, right? Males and females. If you're a male offspring, you only get an X trait from your mother. You only get that trait if she has it. So when we look at this first box, we have a male individual here. He is not, it's not really clear which parent he's getting it from. And it makes more sense to think about it with alleles, right? We know, using even this Punnett square, the same one, that most likely his parents were either heterozygous, were both heterozygous, I'm sorry, because of this recessive trait over here. If it was X-linked, we would see some kind of pattern between the mothers and the children. And there's no pattern here. So we know this is autosomal. And same thing for this one. We can show with alleles that how this is passed on very easily. And we know this is also autosomal. So then if we compare this to the X-linked, I'm going to pull this back a little bit so you can see. We can tell based on the traits that it's really different, right? So if you look at this really carefully, you have a mother here in this first box. She passes her trait on to her son, and they're both fully showing this trait. And then he passes it on to his daughters, all of his daughters, right? So if we think about that, there's a clear pattern between who's getting this trait. It's going from mother to son, back to the daughters, right? From female to male to female. Pedigrees don't confirm that there's a mutation or something wrong with the family. They're literally just a tool for scientists to use to kind of show it. So we would never take this to a family and say, hey, I drew a pedigree showing that you have this trait or you have this disease. But you could use it to try to figure out if they did or not. So based on what we see here, we know it's X-linked because of the pattern female, male, female, right? This one is dominant because of the traits here and how our affected daughters are being affected from their fathers. In this case, we have a recessive trait because we are getting affected sons from an affected mother. Okay, it's kind of the opposite of dominant. And X-linked recessive is a great example of color blindness. Typically, unless multiple people in the family are colorblind, women carry the trait. They're not always showing the trait. If they even carry the trait, they're going to give it to their sons because their sons have to get their X chromosome, right? They only have one X. That means they have to get an X from mom because she has 2. So if she has a mutation for this trait, the son is going to get it. So we know with recessive that whatever she has, they're going to have. Hopefully that makes sense. The second page is for you to kind of practice. It's set up like your test will be. So look at that and practice after you finish this video. And then we're going to move on to a couple other practice problems while time remains. So we have a Huntington's disease case here. When we look at this pedigree, we have an example of the kind of questions you're going to get on your test. So number one, which members of the family above are afflicted with Huntington's disease? All of these individuals are numbered for you, so that's what you need to reference along with the generation number to tell me the individuals. The way we do that is by kind of listing them in that order. So we know red means that they're affected with Huntington's disease. So when we answer this question, who's afflicted, we know generation 1, individual 1 is affected. We know generation 2, individual 2, generation 2, individual 3, generation 2, individual 7, and generation 3, individual 3. And that is everybody in red. Next question. There are no carriers for Huntington's disease. You either have it or you don't. With this in mind, do you think it's caused by a dominant or a recessive trait? So for this one, let's really think about this. You have two parents. One has the trait, one doesn't. When you look at their offspring, in the first generation, you have one, sorry, let me use a different color. 1, 2, 3, 4, 5, 6 children. Out of those 6 children, 3 of them have the trait for Huntington's disease. So if we think about this with alleles, we could think about what mom and dad might have. So let's say it's a dominant trait, right? If dad is showing it because he's dominant and mom is recessive, that would account for why about 50-50 of our traits are dominant and 50-50 are recessive. In this case down here with this marriage, depending on if this was kind of the same situation, you could end up with the same traits. Generally, we would say this is a dominant trait. Next question. How many children did individuals 1, generation 1, individual 1, and generation 1, individual 2 have? So now we are talking about these two at the top. We just kind of counted them before, and we know they have 6. Be really careful not to count any marriages. So you have 2 marriages here. Be really careful not to count those. How many girls did generation 2, individual 1, and generation 2, individual 2 have? So that's this marriage that I've kind of colored up a bunch right here. How many children did they have? They had 3. How many have Huntington's disease? That one circle that's shaded in, that means 1. How are individuals 3, or individuals generation 3, individual 2, and generation 2, individual 4 related? So for that one, we have to count, right? Generation 3, individual 2, generation 2, individual 4. So let's think about this like it's your family, right? If you are this kid, individual 2, you are the children of these people, your mom is here, and over here your mom has a brother. That would be your uncle. Sometimes you might see a pedigree where there's some weird things going on and you have some ancestral family stuff going on. That does happen in pedigrees. So just be aware that you might see that sometimes. And the last one is individual 1, 2. So this guy, I'm going to circle him a lot since we use a lot of color. And 3, 5. So again, if we're this kid right here, and we think about his parentage, these are his parents. His mom has a mom, so that means that's his grandma. Hopefully that makes sense. Let's try one more real quick. Pedigree to the right shows a family for Hitchhiker's thumb. So that basically means, like, if you look at your thumb and you hold it up in front of your face right now, Hitchhiker's thumb goes like way back. I do not have Hitchhiker's thumb, but I could post a picture of it if you want to see it. So we're looking at this and trying to decide, is it dominant or recessive? Hopefully, based on what I've told you, you can look at this and immediately know the answer, because it's a great example of what it means to be recessive, right? So when you have a dominant trait, most of your family is going to show that dominant trait. And this is a great example of that, and how, because of a marriage, and this is exactly kind of what I was talking about before, we'll get there, and because of how these traits were passed on, we have two individuals down here who are the only ones that show that trait. So it is absolutely a recessive trait. And we know that because of how few have it. So let's get into this parentage. How are individuals 3, 1, if you have to ever number them yourselves down, oh, I'm sorry, 3, 1, I was so wrong. This one, 3, 1, and 3, 2 related. So this is complicated. They are paired off by a line, right? Which, if you go back up to the top, that means that they are married. That is not wrong. But if you really think about this individual right here is the daughter of these two people. So these are her grandparents. So she's a granddaughter. This individual over here has two parents of the same grandparents. So that means that they are cousins. So they are cousins and they are married. So this is a case of incest, which is illegal. A big no. So we're going to write both cousins and married. And then the next one is asking how we would name individuals, the two individuals who have Hitchhiker's thumb. So it just wants you to use these number guides to show us what we would call them. So they are both in generation 4. Oops, I'm so sorry. Wrong one. Generation 4, individuals 1 and 3. Name the two individuals that were carriers of Hitchhiker's thumb. So in order for them to have this trait, right, that means both of their parents had to carry the trait. Otherwise, they wouldn't have it, especially if it was recessive. So if we named them, they're both in generation 3. They're individuals 1 and 2 in this case. And is it possible for individual 4-2 to be a carrier? And then why? So if we did this Punnett square real quick, we know that both parents are heterozygous. So when you fill out your Punnett square, you Punnett squares aren't absolute, right? This is, every time you have a child, this is the probability of what traits they could have. So since both of them are carriers, there is a possibility, because of these two individual boxes right here, that they could also be carriers. So the answer is yes, because they pass on their heterozygous trait, to the next generation. So I hope this has helped you. I went kind of fast. And if you have any questions, please let me know.